right, now that we've had an introduction to vector-valued functions, let's talk about how can we do calculus with these functions, specifically thinking about finding derivatives and antiderivatives. All right, let's see. There we go. And so as far as derivatives, how do we find the derivative of a vector-valued function? Well, the answer is we just take the derivative of each of those component functions. So if I want to find the derivative of the function 3ti minus sine of 2tj plus e to the tk, my derivative is going to be a new vector-valued function. So my derivative is going to be a vector. And I just take the derivative of each of those components. So the I component, let's see, we've got a 3t, and the derivative of 3t is just 3. And then for the j component, I have a negative sine of 2t, and so I have to use the chain rule on that. I get negative cosine of 2t, and then times 2. That times 2 is my chain rule. And then finally, the derivative of e to the t is e to the t. And that's my answer. My derivative is a new vector-valued function, 3, negative 2 cosine 2t, and e to the t. And that's it. We can find the second derivative of this function by just taking the derivative of the derivative. And so in the previous example, we found the derivative to be 3 negative 2 cosine 2t e to the t. And so for the second derivative, I just take the derivative of each of those components. So derivative of 3 is 0. And then I have to use the chain rule again on that middle component. So negative 2 times negative sine of 2t. And then again times 2, that's my chain rule. And then derivative of e to the t is e to the t. So I would write my second derivative as the vector-valued function 0 for sine of 2t e to the t. All right, so whether we're taking a first derivative, second derivative, higher derivative, the idea is we just take the derivative of each component function. We can perform vector operations with these derivatives. Again, these derivatives are new vectors, vector functions. So for example, we could find the dot product of r prime and r double prime. And now recall the dot product always gives us a scalar. And so when we take the dot product of these two vectors, or vector-valued functions, we're going to get a function that's not a vector. So there's our definition of the dot product. We take the corresponding components, multiply them together, and then add those products up. So that's why I have on the screen, let's see, we take 3 times 0 plus negative 2 cosine 2t times 4 sine 2t times plus e to the t times e to the t. So I'm just applying my definition of the dot product to these derivatives. And I'll simplify that down. 3 times 0 is just 0. And then negative 2 cosine 2t times 4 sine 2t, that's negative 8 cosine 2t sine 2t. And then finally, e to the t times e to the t. When we multiply, we add the exponents. And so that's how I got the e to the 2t there. And so that expression is my answer. Again, when you're finding the dot product, your answer is not going to be a vector. It's just a function. On this next slide, I have a bunch of properties of derivatives. And so some of these properties should look kind of familiar. They're very similar to when you're working with just ordinary functions, functions that aren't vectors. So the first property here says If you have a constant times a function, to take the derivative, you get the constant times the derivative. Let's see, our second property is the same whether or not you're working with the vector valued functions. If you're taking the derivative of a sum or a difference, you just take the derivative of each piece separately. And then I've got a handful of product rules. 3, 4, and 5 are all product rules. And they're saying if you take the derivative of, so if we look at number 3 first, if you have a function, and notice the f is not in bold, so it's just a function that's not a vector times a vector function, and you want to take its derivative, you can apply the product rule by taking derivative of the first times the second plus derivative of the second times the first. That's the same product rule you've learned in the past. And then number 4 says you can also apply the product rule to a dot product of two vectors. Derivative of the first times the second plus derivative of the second times the first. We can apply the product rule to a cross product as well. I guess the only thing I should point out is when you're taking a cross product, the order matters. In the properties 3 and 4, the order of that multiplication doesn't matter, so if you switch up the orders, it doesn't matter. But with cross products, the order does matter, and so you do want to make sure if you're applying this property, this product rule, whatever is first in your cross product has to be the first thing in the cross products in the product rule. So just make sure you keep the order consistent throughout this property. So again, it's saying our derivative of a cross product, we take derivative of the first cross the second, and then derivative, or I guess it's the first cross, oh no, that should say derivative of the second. Let me fix that real quick. All right, there we go. So it's derivative of the first, derivative of the first times the second plus the first times derivative of the second. And then finally, property number 6 is our chain rule. So if we want to take the derivative of a composition of functions, it's our outside times inside derivative. All right, so let's do some examples. Let's apply some of these properties to some vector valued functions. So I have defined r to be the function t, 5t negative t squared, and u is 6t negative t to the third t, and I'm going to find the derivative of r minus 5u. So we can actually just go ahead and find r prime and u prime. Let's see, r prime would be 1, 5, negative 2t. I just took the derivative of each component. U prime would be 6, negative 3t squared, 1. And then in this first example, we just have a difference of functions. And this 5 is a scalar, so a constant, I should say it's a constant scalar. So we have a constant times a function. And so our derivative is just going to be whatever r prime is, minus 5 times u prime. So we'll take the r prime, which was 1, 5, negative 2t, and we'll subtract 5 times u prime, which was the 6, negative 3t squared, 1. So I distributed the 5 to my u prime, and then I subtracted the corresponding components, and that should give me, let's see, 1 minus 30, this should be a negative 29, and then 5 minus a negative 15t squared, so that's 5 plus 15t squared, and then minus 2t minus 5, okay. So there's my final answer for that derivative. All right, I've got the same two vector valued functions, r and u. Let's find the derivative of r dot u. So find the derivative of a dot product. So there's two different ways you can do this. You can apply the product rule, and I'm going to do that first. So using the product rule, the derivative of r dot u should be r prime dot u plus r dot u prime. Now with dot products, the order doesn't matter, so if you switch around the order, that's fine. I like to be consistent and always just keep the vector valued functions in the same order, but doesn't matter in this case. So the r prime and the u prime are the same as before. We're working with the same functions. So the r prime is still 1, 5, negative 2t. The u prime is still 6, negative 3t squared, 1. And so let's just plug those vectors in. So I'm going to start by computing r prime. So there's my r prime dotted with u. So I'm going to compute the dot product of r prime and the original vector u by multiplying the corresponding components and then adding them together. So let's see, 1 times 6t plus 5 times negative t to the third, and then plus negative 2t times t. That simplifies down to 6t minus 5t to the third minus 2t squared. All right, so that's the first part of my product rule. And then for the second part, I'm going to take r and dot that with u prime. So multiplying those corresponding components together, t times 6, so I get 6t, 5t times negative 3t squared, negative 15t to the third, and then multiply the last two components together to get the negative t squared. So then we're going to take our r prime dotted with u, and we'll add that to the r dotted with u prime. And so I have that written on the top of the screen, and then I'll just go ahead and combine like terms. And so my final answer, notice my final answer is not a vector, because when you take the dot product, you do not get a vector, you end up getting a scalar. So final answer, negative 20t to the third minus 3t squared plus 12t. Now, the purpose of this section is practicing using our product rule. And so when you're doing your homework, I would like you to use the product rule if they ask you to find the derivative of a product, because I want you to get some practice with this. But another way to do this problem is you could actually compute the dot product of the two functions first and then take the derivative of that. And that's a great way to check your work. So if I just take the dot product of r with u, let's see, multiplying those corresponding components together, adding them up, I end up getting a 6t squared minus 5t to the fourth minus t to the third. And you can double check, if you take the derivative of this dot product, it will give you the same answer I got when I used my product rule. So if you just take the derivative one term at a time, get the exact same answer. So that's a great way to check your work. All right, let's do a derivative of a cross product. Same functions r and u, but we're going to find the derivative of r cross u. And I'm going to do this problem using the product rule. So the product rule says I have to take r prime cross u plus r cross u prime. And cross products are the one where the order matters, so make sure you put the r's first and the u second. So I'm going to start by finding r prime cross u. And so I went ahead and I built my determinant. I put r prime directly underneath the I, j's, and k's. And then I took u and put that in the third row. And now I'm ready to compute r prime times u. And so I'm going to go ahead and compute this cross product. So I cover up the I, take the remaining expressions, put them in a little determinant next to the I hat. So 5, negative t to the third, negative 2tt. And then I cover up the column with the j, take the remaining expressions, put them into a determinant for the j component, making sure that one is negative because the signs always alternate. And then finally, cover up the k, put the remaining expressions in the determinant with the k hat, and that one is positive because the signs are always positive, negative, positive. All right, and then we can go through and multiply, let's see, top left times bottom right. So 5t minus, that's going to be a 2t to the fourth I hat. And then for the j, it's going to be a minus because it's negative t, and that's going to become a plus 12t squared. And then for the k component, we get plus negative t to the third minus 30t. So that's r prime cross u, r prime cross u. So first half of our product rule. All right, so I just erased so I had more room and copied down my answer. So there's my answer for r prime cross u. And now I have to do r cross u prime. So I'm going to make sure that I put the function r right underneath my I, j, and k. And then, here we go, u prime goes into the third row. And I'm going to go ahead and expand this using that exact same process. So that everything not under the I is my I component. Everything not under the j is the j. And everything not under the k is the k. And I want to make sure the signs are alternating, positive, negative, positive. And then I can go through, do the same process. So top left times bottom right. So 5t minus 3t to the fourth for my I component. J component would be minus, and then t plus 6t squared. And finally, my k component, negative 3 to the t to the third minus 30t. And so let me make some room, erase that, write that down. So we've figured out r cross u prime is that vector valued function. And then finally, the product rule says we add together those two cross products. And so I'm going to add those together by just adding the corresponding components. So I did 5t minus 2t to the fourth plus 5t minus 3t to the fourth, and that's how I got the 10t minus 5t to the fourth. That's my I component. And then I distributed those negatives for the j components and then added the terms together to get the negative 2t minus 18t squared j. And then added the k components together, and that's how I got the negative 4t to the third, negative 60t. And that's my final answer. Notice that when I'm taking the derivative of a cross product, my answer is a vector valued function because cross products give us vectors, unlike when we took the derivative of our dot product. I think the other thing I'd like to point out is notice I have to have parentheses because our component functions have more than one term. And so if you don't have parentheses, it's not clear what is a part of each component. Now, for this problem, you could also compute the cross product first and then take the derivative of that vector valued function. That should give you the exact same answer as well. However, when you are working on your homework in this section, I do want you to practice using the product rule. That's really kind of the purpose of these problems for now. All right, so we know how to find the derivative of a vector valued function, but I want to pause for a minute and think a little bit about what is that derivative giving us information about. Back in Calc 1, when you were first introduced to derivatives, hopefully you learned that the derivative is going to give you the slope of the tangent line. So if you were to draw a tangent line, that derivative is going to give you its slope. The derivative of a vector valued function also gives us information about what is tangent to that vector valued function. And in this case, it's going to give us information about the tangent vector. And so on this screen, I have an image where I have a plane curve. So that would be an r of t, a vector valued function. And then those little blue arrows are supposed to represent the tangent vectors. So they should just be touching the curve, just like a tangent line. And they are pointing in the direction of the motion. And so if we want to find a tangent vector, we just need to take the derivative of our vector valued function. Now, in many cases, we might actually want to find a unit tangent vector. And if we recall back to the previous chapter, a unit vector has a magnitude of 1. So our unit tangent vector, which we are going to always use the letter t for, is going to be our derivative divided by the magnitude of our derivative. So for example, if I have the vector valued function r equals t squared t 4/3, and I want to find the vector t, that's that notation. If you just are asked to find this vector t, that's asking you to find the unit tangent vector for this function. So let's just focus on part A first. Or I guess the first of my part A's first. So to find my unit tangent vector, I'm going to find the derivative. I'm going to find r prime. So I take the derivative of my component functions. That gives me 2t, 1, 0. And then to turn this into a unit vector, I'm going to find the magnitude of that derivative. And so to find the magnitude, I take the square root of the sum of the components squared. And so in this case, I get the square root of 4t squared plus 1. That cannot be simplified any further because of this plus sign right here. Can't distribute square roots when you have sums or differences. So there's the magnitude of my derivative. And so that means my unit tangent vector is, I'm going to take my derivative and I'm going to divide it by the square root of 4t squared plus 1. And so to do that, I just went through and I divided each component by that square root. And so I got a new vector, 2t over square root of 4t squared plus 1. And then 1 over square root of 4t squared plus 1. And then for the last component, it'll just still be 0. So there's part A, my unit tangent vector. And then the second part, part B, which I guess I have labeled as A again. You know, PowerPoint has been doing that. I copy and paste things over and it changes it all to A's, and I just left it like that. So you could call that part B. So if we want to find our unit tangent vector at the point 1, 1, 4/3, They're just asking us to find this vector at a specific time. And so if I take a look at my original vector function, what t value gives me the point 1, 1, 4/3? In this case, you might be able to see just by looking at it. But if you couldn't, you would just say, okay, when does t squared equal 1? And then I guess t would equal 1. And 4/3 equals 4/3. You can see that that's only true if t is 1. Okay, so we are at this point when t is 1. And so in this part of the problem, they're basically just asking you to plug t equals 1 into your unit tangent vector. And so I'm going to go ahead and do that. So I just put 1 in for all of the t's. And I got a vector 2 over root 5 plus 1 over root 5, comma 0. So there's my unit tangent vector at the point 1, 1, 4/3. Finally, the last thing they want us to do in this problem is find the equation of the line tangent to r at the point 1, 1, 4/3. So now we're going to have to use information that we've learned in the previous chapter and apply that here. So my tangent vector goes in the same direction as my tangent line. My tangent vector is actually my direction vector. And then I am given a point for that line as well. And so I'm going to go ahead and write my equation in parametric form. That's how we've been writing equations of lines in space. And so my point was, here it is, 1, 1, 4/3. And then my direction vector is my tangent vector. And so I got x equal 1 plus 2 over root 5t, y equals 1 plus 1 over root 5t, and then z equals 4/3 plus 0t. We don't need to write that plus 0t. We can just use z equal 4/3. And so this answer that I'm circling right now is perfect. That is the correct answer. That is the equation of a line tangent to this function, or this, I guess it's a space curve at 1, 1, 4/3. However, when you are coming up with your direction vector, you don't have to use the unit vector. A direction vector doesn't have to have a magnitude of 1. And so if you want your equation to look a little bit nicer, you could just take the tangent vector and say that, okay, well, I'm just going to go through and multiply everything by root 5 just to clear those fractions and make it look a little bit better. Let me actually write that down for you. So you could just say, okay, the direction vector, I want it to look nice and have whole numbers. It just has to be in the same direction as my unit tangent vector. So I'm going to multiply everything by root 5, and I get 2, 1, 0. And so you could use 2, 1, 0 as your direction vector. And then your parametric equations would be x equal 1 plus 2t, y equals 1 plus t, and z equals 4/3 plus 0t, or just 4/3. Either of these answers are fine. It doesn't matter which one you use. I guess, though, if I was going to have to do more math with these parametric equations, I probably want to use the second form. It's just those numbers look a little bit easier to work with, but it doesn't matter. So really, the point I wanted to make here is when you're writing your equation of a line, your direction vector just has to point in the same direction as that unit tangent vector. It doesn't have to have a magnitude of 1. Okay, but both of the answers I have circled are completely correct for that third part of this problem. All right, so moving on, we learned we can take the derivative of a vector valued function, just one component at a time. Same is true with antiderivatives. We can find both indefinite and definite integrals of vector valued functions by integrating each component function. And again, this can be either definite or indefinite integrals. So let's do an example. Let's try to find the antiderivative of the following vector valued function: 1 over 2ti plus square root of tj plus 1 over 1 plus t squared k. So to find this antiderivative, we just have to integrate each component function, and our answer will be a new vector valued function. So the antiderivative of 1 over 2t, I'll pull the constant out front. So now I have 1/2 antiderivative of 1 over t. I just have memorized antiderivative of 1 over t is natural log absolute value of t. So I get 1/2 ln t plus c plus a constant. Second component function, let's integrate square root of t. It's the same thing as t to the 1/2. Add 1 to the exponent and divide. And so I get 2/3 t to the 3/2, and again, plus a constant. Last one, if I integrate 1 over 1 plus t squared, I just have memorized that that is arctangent of t plus a constant. I suppose if you didn't have it memorized, you could use a trig substitution. That sounds really hard. I think it's easier to just remember 1 over 1 plus t squared gives you an arctangent. So putting all of this together, my answer is going to be a new vector valued function. And so technically my answer is going to look something like what I have written on the top of the screen. It's a new vector valued function. And we do get a constant in each one of these components. So when we find our antiderivative, we always have a plus c. And so we get a constant in each one of the components. And we really should distinguish between the three constants because they may not all be the same number. So I'm going to call the first one, I'm going to put a plus c1, and then in the second one, I put, let's see, plus c2, and then in the third component, plus c3. So just to distinguish between the different component, or different constants in the different components. So at the top of the screen, this is my answer right here. So I found the antiderivative. Oops, I did not mean to erase all that. Oh well. I have another slide with the answer on it. That's okay. So I found my antiderivative and I wrote it as a vector in component form. Now, a slightly more compact way of writing this answer is to create a constant vector. So you can just create a vector called c that contains all your constants of integration. So I'm going to say vector c is a vector that contains constant 1, constant 2, constant 3. And then I can just write my answer by listing my antiderivatives and then just tacking on plus constant vector. So that's a slightly different way of writing the answer. Either format is fine. I personally like this second format because then you just tack on a plus c at the end. Just make sure it's a plus vector c. All right, so to summarize, if we're finding an antiderivative, we just integrate each of the component functions separately. Our answer is going to be a vector valued function, and then we'll tack on a plus c, which is also a vector. All right, let's finish by finding a definite integral. So we can also find definite integrals of vector valued functions. And same process, we integrate each component function individually. And those answers give us the components of our final answer. So we're going to start by finding the antiderivative of the first component function. So we're going to find the antiderivative of secant tangent. And that one I just have memorized. I know it's secant because the derivative of secant is secant tangent. My bounds of integration are 0 and pi over 4. So I'm going to plug in pi over 4. I'm going to plug in 0 and then subtract them. So secant of pi over 4 minus secant 0. I got root 2 minus 1. And then I'll do the same thing with my other component functions. So I'm going to integrate tangent t. And that one I also have memorized. It's negative natural log of cosine t. And then I'll plug in my bounds of integration and subtract. So let's see, I get negative natural log of cosine of pi over 4 minus a minus, so plus natural log of cosine of 0. So negative natural log of root 2 over 2. And then I guess it should be, this should be a plus ln 1. Although natural log of 1 is just 0. So final answer, negative natural log root 2 over 2. All right, one more component. We are going to integrate sine t cosine t. And so there's several ways to do this one. This one I don't have memorized, so I'm going to have to do a little bit of work. And the little bit of work I'm going to do is a u substitution. I'm going to let u equal sine of t, because then my du would be cosine t dt. So derivative of sine is cosine. And that makes this integral turn into a u du. So the cosine t dt is my du, sine of t is my u, and that's something I can integrate. Antiderivative of u is u squared over 2. So in this context, it becomes sine squared of t over 2. And then I'm going to go ahead and plug those bounds of integration in. So sine of pi over 4 divided by 2 minus sine of 0 divided by 2. I ended up getting 1/4 when I did those computations. So finally, these answers, these 3 values that I've gotten when I found those definite integrals, give me my components of my answer. And so my final answer is the vector root 2 minus 1, negative natural log of root 2 over 2, put an extra parenthesis there, and 1/4. So whether you're taking the derivative or you're integrating a vector valued function, your answer is going to be a vector. The only time you don't get a vector is if you're working with a dot product, because dot products give you scalars instead of vectors. All right, that was my last example. As always, please let me know if you have any questions.